All right, so now that we have defined the two axes, the radial and transverse axis, let's go ahead and start defining our position, velocities, and acceleration. In this video, positions and velocities. So position is very easy. Position. So as you can see, by definition, the radial axis points from the origin to the location of the particle. So this vector r, oh, why did I do this? R, which is our position vector, is by definition the distance, or let's call it just r, in the direction of radial frame. And that is the position. However much distance from the origin toward the location of the particle, that is your position vector. Fairly simple. For velocity, similar to what we had done before, we can say v equals time derivative of position. You can take derivative of the top equation. It's r dot ur plus r ur dot, and follow the same logic we had in the normal tangential frame to figure out what this term is. I'm not going to derive that, but it is fairly straightforward. And what you end up with is v equals r dot ur plus r theta dot u theta. Feel free to follow the derivation in textbook. I'm not going to do it here. Actually, my figure doesn't look the best. Let me quickly clean up, make it slightly better so you see. Let's call this origin. Let's call particle here. This is ur u theta along that direction. This was r, vector r, and the length is r. So this theta that we have defined, this one, is the time derivative of how much this arm, this lever arm, is turning. We can call this angular velocity. Velocity is the rate of change of angle with respect to time. And now we can see the velocity has two components. Let's break them down, see what they actually mean. Let me draw a box around it so you know it is important. So one thing to always remember, velocity is tangent to the path. Velocity has to be tangent to the path. That's the definition, or a very fundamental property. Now you see velocity, v, has two components. Some radial component along the radial axis. Oh, why did I t? Radial axis, plus some component in the transverse direction along the transverse axis. And this one is r dot, this one is r theta dot. And these two should add up together such that we have this tangential velocity to the path. How does that work? And what each one means. So consider two simple examples. One is if this is your origin, your radial axis. Assume the particle is just moving along that axis, no rotation. So your distance r is changing, which means along that axis you have some radial components of velocity just because the distance is changing. For the other one, make it bigger. Maybe it is easier to consider another extreme case where your path is a perfect circle. So you're here. The distance always remains constant, but you have some velocity, and that is due to change in the angle. So however distance you are multiplied by the angular velocity, the rate of change of the angle, gives you this transverse component, VR. So the radial component relates to how fast your distance from the origin is changing. Transverse component is related to how fast the angle is changing. And these two components of velocity add up together to give you the total velocity vector, which happens to be always tangent to the path. Oh, what did I do? So, that is, I think, it. Something always to remember. What happened? Why did this one froze? My iPad froze. Come on. Yep, it is frozen, so I'll stop talking now. The only thing I wanted to say, I wanted to write down, but I cannot. And I'll just say it. That is, if you want to find the magnitude of the velocity or the speed, you have to consider both of these components, and the magnitude is the square root of the radial component squared plus the transverse component squared. So that is position and velocity. Let's stop it there. In the next video, we'll look at acceleration, which is a lot more fun, and a few other tiny stuff, and we finish this section. So I'll see you in the next video.